Welcome back. We're into week 6, and our labs go with the week, so this is lab 6, and it's called the Atwood machine. And this is the picture of George Atwood, 1784, when he came up with this little machine. Now, this is a drawing, an illustration of like an Atwood machine that you would buy from the company to do in the lab. And it is really complicated. We've got this down. It is a piece of cake now, how to do the Atwood machine. But anyway, you can see there's a pulley up here at the top, and there's two masses. The one mass, B, right here, you can see. And then over on the other side is mass A. I'm not quite sure what this device was used for right here. But anyway, one side, well, you can make one side equal to the other side. In fact, I have it set up right here, so I can show you that. So instead of having one pulley, we have two pulleys in order to keep the masses from knocking into each other. So on the Atwood machine that is shown on the slide, that was a really big pulley. Well, we can use a little pulley if we separate them by a certain distance and keep the pulley so it doesn't have much of an effect on the experiment. When we get into rotational motion, you'll find out that the pulley has this property that you have to give it a little force too to make it turn. But if you can make it really, really light and super easy to turn, we can ignore it. So keep that in mind. Okay, so anyway, I have 25 grams over on this side. I got a nice piece of fishing line, goes over the top. And on the other side, I have the equal amount of weight. Okay, so you can see when I go and I put it somewhere, it just stays. And that's because the forces are balanced. Basically, Atwood machine is a tug of war. Okay, it's one side pulling on the other side through the tension force in the string. And the gravity is the force from outside that's trying to but if you make the masses equal, then it's balanced. So you can see, I can put it anywhere I want, and you see the net force is 0. Okay, now the nice thing about Newton's first law, it says an object in motion will stay in motion. Object at rest will stay at rest. So I can give this guy like a little push, and you can see it goes pretty well constant motion. Pretty well. But remember, there's still some friction in it, but you can see it's pretty much going at a nice constant clip right there. So Atwood invented this machine to study Newton's laws and to allow students to easily study Newton's laws in the lab. All right, so let's go back to the screen over here and show you what the forces are acting on the system. All right, so all of Newton's laws are going to be demonstrated in this one device. Now, I already demonstrated Newton's first law. Now, the second law says if there's a net force acting on an object, the object will accelerate in the direction of the force. And the third law says that forces always occur in equal and opposite pairs. When we say equal and opposite, we mean the force has to be identical. So in this picture here, you can see there's a tension that's pulling up on this mass M2. Well, over on the other side, there's a tension in the string that's pulling up on object 1. So you see, they are identical forces, tension and tension. They can't be like tension and weight. That is not Newton's third law. So this tension is equal and opposite to that tension. And what we normally do is we put the force, the object that's acting on this object. So object 2, mass 2, is pulling on object 1 with the tension through the string. Likewise over here, this object 2 is being pulled up by object 1, and that is its tension. And these two forces are equal but opposite according to Newton's third law. All right, what about weight? Well, you see, gravity is pulling on this thing, M2. Well, what's gravity? Well, gravity is from the Earth. And the symbol for the Earth is a circle with a cross in there. May the Lord be with you. All right, so that is the Earth acting on object 2 right there, trying to pull it to the ground. Just like this right now, this feeling friction, static friction of my fingers holding it up, and then gravity down. So if I let go of it, you see it goes into free fall, which would be the force of the Earth pulling on the pointer right here. So this guy's feeling the pull of the Earth on its mass, and over here, this is the Earth pulling on that object. Now, we don't see the opposite force because it's not important to what we're doing, and the Earth happens to be so massive that the puny little force of mass 1 pulling up on the Earth is not important, is not going to affect our experiment in any way. Okay, same thing over here. So the equal opposite forces are the objects pulling up on the Earth. Okay? So we're just interested in looking at this tug of war over here. Now, if this side is more massive, you can see it's got a longer arrow right there. And remember, weight is calculated by mass times gravity. So M1 times G is larger than M2 times G. All right. Now, if you look at the forces, this is bigger than that, so this is going to accelerate like that. All right. Now, this is equal to that. All right. And this is smaller than that. So you see, there's a net force from the outside. These cancel out. So if you go all the way around this string right here, these two guys cancel out. This one is pulling this way on the string, and this one's pulling the opposite way. Well, since the motion's going to be towards the more massive object, we call that the x direction. This is basically the x-axis, but it's wrapped around a pulley. I like to call it a limp x-axis because the x-axis is wrapped around the pulley. So this is the negative x direction, this is the positive x direction. So on this side, the weight, the pull of the Earth, is weaker than the weight on this side, and so M1 wins out, and the whole apparatus will accelerate in the direction of weight 1 over there, like that. And we'll demonstrate that when we talk about the experimental setup in a minute. But anyway, this is the acceleration vector, and these two objects accelerate at the same rate depending on what the net force is. And the net force is just due to the differences in the weights. So this would be a positive weight minus a negative weight, and so when you add those up, they subtract from each other, and that will cause M1 plus M2 to accelerate at A. All right. That's it right there. So there's some notes for you. You can read through this when you do the video, and you'll see exactly the words that we've been talking about right here. But it's really important that you get this idea. This is the x-axis, like that. So this is the negative x direction, this is the positive x direction. So you can see T21 is in the negative x direction, T12 is in the positive x direction. So you see they're equal but opposite. All right. Now, here are the equations for each. I'm looking at each object now. I'm using Newton's second law. Newton's second law says an object, so pick an object, so we got M1 or M2, an object acted upon by a net force will accelerate in the direction of the net force. Okay, so look at M1. What are the forces acting on M1? Well, it's the weight of the Earth, M1 times G, minus the tension, T21, and that's going to cause M1 to accelerate at A. And that's it right there. So you see the weight minus the tension equals MA, M1 times A. Now, over on this side, what do we have? We've got the net force acting on M2. Well, that's tension 1, 2. Remember, it's in the positive direction. Minus the weight is in the negative direction, equals M2 times A. Now that's two equations and two unknowns. This is a control, okay? This over here is a control, this is a control. and then you get the acceleration, and then you get the tension. So you can solve those simultaneously, and this is the result right there. And this is what we're really going to be studying in the lab today. All right, let me see. Do I have another picture? Nope, that's it. So we'll come right back to there. I can do really quickly on the board. Let me just do this. Let's suppose we looked at the whole system. So we start over on the left side, over there. So what do we have? We got W1 positive minus T21. Okay, we go all the way over the top, and then we got plus T12, and then minus W2, and that's going to cause both of them to accelerate. So M1 plus M2 times A. And this is the tug-of-war equation. See, these are the two guys pulling on each other, and we treat it as one whole system. And you see, but according to Newton's third law, that goes out, that's equal to 0 right there. So if you're only interested in the acceleration, this goes really quick. And so remember, this is M1 minus M2, all times G. Remember, weight is equal to mass times gravity. And this is equal to M1 plus M2 times the acceleration. So when you solve for the acceleration, this goes over to the other side. So you get M1 minus M2. That's the tug of war, the difference in the weights, divided by M1 plus M2. And then times gravity. Okay? And this is a constant. It's not a control. We're not changing gravity in our experiment. That's a constant. Okay? All right, so that's it. That's the background to the Atwood machine, which is nothing more than an experimental apparatus for demonstrating Newton's 3 laws. So peace out. May the Lord be with you. And we'll go on to the experiment next. Over and out.